Hello everyone and welcome to our today's class. It's our first lesson on the 7th topic of Form 2 work, which is called Hooke's Law. So as usual, let me commence by giving you the quote of the day, which states that we have 2 ears and 1 mouth so that we can listen twice as much as we speak. Unfortunately, most of us usually speak twice as much as they listen. So we'll discuss that quote at the end of our class today. So today we are beginning with a few definitions that we need to familiarize ourselves with that will be very essential in understanding the topic Hooke's Law. So the first term is called strength. So these are just the properties that describe various materials. Now, what is strength? Strength refers to the ability of a material to resist breakage when under a stretching, compressing, or shearing force. Also remember that a strong material is one which can withstand a large force without breaking. Our second term is called stiffness, which refers to the resistance a material offers to forces which tend to change its shape or size. And also remember that stiff materials are usually not flexible and usually resist bending. Our third term is called ductility, which refers to the quality of a material which leads to permanent change of size and shape. Then we are also saying that materials which elongate considerably under stretching forces and undergo plastic deformation until they break are called ductile materials. So we are saying that materials which elongate considerably under stretching forces and undergo plastic deformation until they break are usually known as ductile materials. And examples of ductile materials are: 1, we have lead; 2, we have copper; 3, we have iron; and plasticine. Now, ductile materials can be rolled into shapes, into sheets, drawn into wires, or worked into other useful shapes without breaking. They are therefore used or applied in the making of implements such as staples, rivets, and even paper clips. Our fourth term is called brittleness, which refers to the quality of a material which leads to breakage just after elastic limit is reached. We are also saying that brittle materials are usually fragile and do not undergo any noticeable extension on stretching, but snap suddenly without a warning. An example of brittle materials, we have a blackboard chalk, we also have a brick, we have a cast iron, a glass, and even a dry biscuit. So remember, we are saying that brittle materials are those materials which are usually fragile and do not undergo any noticeable extension on stretching, but they snap suddenly without a warning. So to snap is just to break immediately without actually having to stretch. Like for the case of a dry biscuit, whenever you try to stretch a dry biscuit from both ends, it usually breaks or snaps immediately without even stretching. So such a material is called a brittle. Such case, another example of such, we have talked of also the blackboard chalk. Whenever you try to stretch a blackboard chalk, it usually breaks or snaps immediately without stretching or without warning. So such materials are called brittle materials. Then our last term is called elasticity, which refers to the ability of a material to recover its original shape and size after the force causing deformation is removed. Then we are also saying that a material which does not recover but is deformed permanently, for example plasticine, is said to be plastic. So in short, we are saying that the plastic materials are the opposite of elastic materials, because elastic materials, these are materials which can easily recover their original shape and size after the force causing deformation is removed. On the other hand, plastic materials, these are materials which do not recover but is deformed permanently. An example of plastic material is plasticine. Now we have other materials, for example, rubber band, spring, and metal wires, which can regain their shape when the forces causing deformation is withdrawn or removed. Such materials, we have said, they are called elastic materials. So next we look at stretching of materials, and to understand that we will describe an experiment which usually describes the Hooke's Law. So remember, we are saying that Hooke's Law was discovered by an English scientist who was called Robert Hooke. So because of his second name, that is Hooke, then we derived the name, or the name of the law, which is the Hooke's Law. So in this experiment, there are various apparatus that you will need. One, you will need a spiral spring with a pointer. This is our spiral spring, of course, with a pointer at the end. You will also need a meter rule. This is our meter rule. So just a point to note that a meter rule will always run from the 0 centimeter mark to the 100 centimeter mark. We also need a retort stand. This is our retort stand, of course, to support our ruler, our meter rule, and also the spring together with its pointer. Then we also need 2 sets of clamps and bosses. So these are our clamps and bosses, which actually clips or holds our ruler upright and also the spring in position. Then we also need 20-gram masses. So these are what we are calling our 20-gram mass. This is also a 20-gram mass. So in this experiment, the first procedure is to arrange the apparatus as shown below. That is, you hold the ruler upright, of course, with the 0 mark upwards, and the spring also in position, of course, with a hook. So in the second step, you suspend one of the masses at the end of the spring and not the position of the new position of the pointer. So even before you start the experiment, actually you note the position of the pointer. That is the mark where the pointer is reading on the meter rule, even before attaching any mass. Like in our experiment, we are saying that when the mass on the spring is 0, or when no mass is hooked on the spring, we are saying that our pointer is reading the 30 centimeter mark. So when there is no mass on the spring, our pointer is at the 30 centimeter mark. So that represents our initial scale reading. So we are saying that our initial scale reading is 30 centimeter mark, which if you convert into meters, remember 100 centimeters will always be equal to 1 meter, or about 30 centimeters. So it will be 30 centimeters divided by 100 centimeter. So you obtain actually 0.3 meter. So we are taking 0.3 meter or 30 centimeter as our initial reading of the pointer. That is when no mass is attached. So when 0 mass is attached, it means the force, also the stretching force, is actually 0, because remember, it is the masses which causes the spring to stretch. So that means when the spring has no mass and you are assuming the weight of the spring is negligible, so it means actually the stretching force will be 0, because you take a mass of 0 times gravity of 10, you will always obtain 0. Then you are saying that your initial reading is 30 meter, and therefore the 30 centimeter or 0.3 meter, therefore the extension is 0, or the spring has not extended because there is no mass attached. So in the second step, we now attach one mass, that is a 20-gram mass. So when we attach a 20-gram mass, of course we expect the pointer to move slightly downwards due to the weight that has been added. So if a mass of 20 gram is added, remember 20 gram is equivalent to 0.02 kilogram, because remember that 1,000 grams are equivalent to 1 kilogram. So what about 20 grams? So it will be 20 grams divided by 1,000 grams times 1 kilogram. So if you divide 20 divided by 1,000, you'll obtain 0.02 kilogram, so which is our mass. Therefore, the force applied will be mass times gravity, which is 0.02 times gravity. Gravity, we usually take it as 10 Newton per kilogram. So you take 0.02 times 10, you'll actually obtain 0.2 Newton. Now, somebody could be asking him or herself, why are we converting the mass in kilogram? The reason is because kilogram are actually the SI unit of the mass. So remember, we said that in physics, whenever you are doing any calculation, it is always important to ensure that all quantities are in their respective SI unit. Remember also for this case, the SI unit for length is the meter. That's why we are converting the 30 centimeter into meter, so that we are working with all quantities while they are in their respective SI units. So in the third step, you add another 20 gram mass. So remember, if this is 20 gram mass, this is also 20 gram mass. It means the total mass acting on that particular spring will be 20 gram plus 20 gram, which is actually 40 gram. So you convert 40 gram into kilogram, you'll obtain 0.04 kilogram. Therefore, the force applied, the force is mass times gravity, so it will be 0.04 times 10, which is gravity, so you obtain 0.4 Newton. Then we are saying that when there is one mass attached, we observe the pointer to be at the 40 centimeter mark. So that means that the 40 centimeter mark, so that is 0.4 meters. Therefore, the extension. So remember, the extension is obtained by taking the final value minus the initial value. So our initial value was 0.3 meter. Our final value, that is when only one mass of 20 gram is attached, is at 0.4 meter mark, or at the 40 centimeter mark. Therefore, our extension will be the final reading minus the initial reading. So 0.4 minus 0.1, therefore you obtain our extension as 0.1 meter. Then we are saying that when another mass is added, that is when we have 20 gram plus 20 gram, which is 40 gram, it is observed that the spring pointer moves from the 40 centimeter mark to the 50 centimeter mark. So the pointer reading when two masses of 20 gram or the 40 gram mass is attached, our scale reading, our pointer is at the 50 centimeter mark, which is of course 0.5 meter mark. And therefore our extension, remember the extension we've said you take the final reading minus the initial reading. So the final reading of our pointer is 0.5 meter. The initial reading of the pointer, that is when no mass was attached, was 0.3 meter. So you take 0.5 meter minus 0.3 meter, you'll actually obtain 0.2 meter. Then the fourth step, you attach another third mass of 20 grams. So when there are three masses of 20 grams, it means the total mass will be 20 gram plus 20 gram plus the third 20 gram. So 20 plus 20 plus 20, you obtain 60 gram. Then 60 gram into kilogram, you'll obtain 60 divided by 1000, which is 0.06 kilogram. Therefore, the force applied is mass times gravity. The mass is 0.06 kilogram. The gravity is 10 Newton per kilogram. So 0.06 times 10, you'll obtain 0.6 Newton, which is the stretching force. Then we are also observing that when a mass of 60 gram is attached, actually the pointer moves to the 60 centimeter mark. That is, the pointer moves from the 50 centimeter mark to the 60 centimeter mark. So 60 centimeters in meters, you'll obtain 0.6 meter, and therefore it means our stretching force will be, so remember the extension. The extension is usually obtained by taking the final reading minus the initial reading. That is when no mass was attached. So you take 0.6 meter, you less or you subtract 0.3 meter, you'll actually obtain 0.3 meter. So that becomes our extension. Then of course, after obtaining those values, you draw a graph of force against extension. So the force of course is in Newton, because those are the SI unit of force. Then our extension is in meters, because that is the SI unit of length. So you just plot your graph. You can begin with when the mass is when the force is 0, the extension is also 0. So when you plot here 0, 0, actually you'll have a mark here. When the stretching force is 0.2, the extension is 0.1. So I expect 0.2 to be somewhere here, then 0.1 to be somewhere here. So where the 0.2 and the 0.1 meet, actually you put a star there or a dot there. Then you go to the next 0.4. 0.4 could be somewhere here. Then the 0.4 is corresponding with an extension of 0.2. So 0.4 with 0.2, the mark is likely to be somewhere here. Then of course the last one, 0.6 Newton, corresponds with an extension of 0.3. So 0.6 is likely to be here. Then 0.3 is maybe somewhere here. So where the two marks actually meet is our point, which is somewhere here. Then after that, of course, you are using a ruler. You join the points in a straight line. So this is the graph that will be expected. So whenever you obtain a force extension graph, which is a straight line graph from the origin, as shown here, so this one simply interprets or says that actually the force is directly proportional to the extension. That is to mean that whenever the values of forces are increased, or when more masses are added, then the extension is also increasing. So as you can see, when no mass is attached, the force applied is 0, the extension is 0. When we increase the mass to 20 grams, the force applied is 0.2, the extension also increases to 0.2. When we add the mass to 40 grams, the force applied is 0.4, the extension also increases to 0.2. So you can actually clearly see that whenever the stretching force is increased, or whenever the masses are increased, the extension is also increasing. That is from 0 to 0.2 to 0.4 to 0.6. And the extension is also increasing to 0 to 0.1 to 0.2 to 0.3. So we can easily conclude that the force and the extension are directly proportional to each other. Remember, when quantities are directly proportional to each other, it means also when you reduce one quantity, it also causes a reduction in the other quantity. So force and extension clearly is a straight line graph which simplifies their direct proportionality. So whenever you double the force, the extension will also be doubled. Whenever you halve the forces, the extension will also be halved. But this is the case whereby the elastic limit is not exceeded. That is, when the masses added are taken care of such that they do not cause the spring to go into a state of permanent stretching. So when the Hooke's law is obeyed, that is when the spring is obeying the Hooke's law, or when the force is directly proportional to the extension such that there is no permanent deformation, then this is the expected graph, a straight line graph. Now, there are other cases whereby somebody can add a lot of mass. For example, when you add maybe a mass of 600 grams, and the spring constant does not allow the spring to stretch to such levels and actually regain its original position, when excess mass is added, the spring will stretch permanently. That is, when the masses are removed, the spring will not come back into its original position. Such a state, we call it permanent deformation. So when excess masses are added, it means whenever you continue increasing the forces, actually the extension will still remain constant because the spring has reached its maximum point of extension. So this point whereby even with further addition of the forces or the masses does not correspond to an increase in the extension, this point is called the elastic limit. Such a point, we call it the elastic limit. So OP, this is the position from O to P, is representing what we call a permanent stretching, or what we call permanent extension of the spring. Then point E is called the elastic limit. That is, elastic limit, this is a point beyond which further extension causes permanent extension or permanent deformation or permanent deformation. So we are saying that point E is called the elastic limit, this point E, and point B, which is beyond the elastic limit, we call it the yield point. That is yield, spelling is Y-I-E-L-D, the yield point. So if you are told to explain this, what happens between these points in this graph, you simply says from point O to point E, that is between OE, actually the spring is obeying the Hooke's law. It is obeying the Hooke's law. Alternatively, you can say that between point O and E, the force is varying directly proportional to the extension. However, at point E, that is what we are calling the elastic limit. The elastic limit. That is a point beyond which further adding of the forces does not correspond to extension, or a point beyond which the spring undergoes what we call permanent extension or permanent deformation. Then between point E and B, that is between point E and B, where permanent extension is occurring, we say that between point E and B, the material does not regain back its size or permanent extension occurs. Then at point B, which is the yield point, this is the yield point. Beyond this point, the material actually breaks. Beyond point B, the material breaks. So I've said that if you are told to explain this graph, you would simply say between point O and E, actually Hooke's law is obeyed, or force is directly proportional to the extension. That is between point O and E, Hooke's law is obeyed. Then at point E, this is what we call the elastic limit. At point E is the elastic limit. Then what happens between point E and B? This is where material does not regain back its original size, or the material undergoes what we call permanent extension. Then at point B, this is the yield point. So the yield point, this is the yield point. Beyond this point, actually the material breaks. So beyond point B, which is our yield point, the material breaks or snaps. So that is how we explain the two graphs. Actually, this one simply shows that the extension force is directly proportional to the stretching force. The next we look at what we call the Hooke's law. So we have already said earlier that Hooke's law was discovered by an English scientist in the year 1660, who was called Robert Hooke. So because of his second name, that is Hooke's, we obtained the Hooke's law. Now the Hooke's law states that for a helical spring, now what do we mean by the term a helical spring? A helical spring, the word helical simply means coiled or spiral, or like in a screw shaped. That is those windings of the screw. So we can just call it a coiled or a spiral spring. So the Hooke's law states that for a helical spring or other elastic material, the extension is directly proportional to the stretching force, provided the elastic limit is not exceeded. To exceed means to surpass or to go beyond. So provided the point of the elastic limit, that is a point where the material undergoes permanent extension or permanent deformation, provided that that point is not exceeded, then the Hooke's law states that actually the extension force will be directly proportional to the stretching force. So mathematically, when we talk of direct proportionality, it simply means that an increase in one quantity corresponds to an increase in the other quantity, and also a reduction in one quantity will also lead to a reduction in the other quantity. So mathematically, we are saying that the extension is directly proportional to the stretching force. So mathematically, this is how we can express this particular statement. The extension, we are denoting it by small e. Then the stretching force, we are denoting it by capital F. Then this sign here is what we are calling the direct proportionality symbol. This is our direct proportionality symbol. So clearly you can see that the stretching force is directly proportional to the extension, which also means that the extension is also directly proportional to the stretching force. So for a helical spring or other elastic material, the extension, so this is our extension E, is directly proportional. This is what representing the direct proportionality, this symbol here, to the stretching force. Stretching force, we are denoting it by F. That is provided the elastic limit is not exceeded. Now, mathematically, to remove this proportionality symbol, we usually introduce equal signs with a constant. Remember, a constant can be any value. For example, capital C. For example, even T. For example, also K. Like for this case, we are taking K to be our constant. So when we remove the proportionality symbol, introduce equal sign with a constant, such that we can write this as force is equals to. So this one is substituted with equal sign with a constant. So we can say that force is equals to KE. So to make K the subject of the formula, we'll divide both sides by E. So of course the E with E on this side will cancel, so we remain with K alone. So on this other side we'll have force over E. So mathematically we are saying that K will be equal to F over E. Now from our previous graph, which was a straight line graph, that is for a Hooke's law material, or a material that obeys the Hooke's law, or where the force is directly proportional to the extension. So we have this graph of force against extension. Now whenever we try to find the gradient of this graph, remember mathematically we usually say that the gradient is given by the change in y over change in x, whereby y represents the vertical axis and the x represents the horizontal axis. So if it was in mathematics, we'll say change in y over change in x will be equal to the gradient. But what is holding our change in y is the force, and what is holding our change in x is the extension. So the change in vertical positions, or change in force, or change in y is delta F. This is what we are calling the delta, or this small triangle represents a change in force. That is the force at this point minus the force at this lower point. Then delta E represents the change in extension. That is the extension between this point and this other point. So the gradient will be equal to change in force, or the change in y. That is the change of values in the vertical axis divided by the change of values in the horizontal axis, or change in x. So the horizontal axis is having the extension, therefore the gradient will be change in force divided by change in extension, which we can easily denote by change in delta F divided by change in delta E. So remember, F is in Newton, E is in meters, therefore the units of the gradient will be Newton per meter, or Newton meter power -1, according to the laws of indices. Now, but we discover here that change in F over change in E is actually our K here. And remember, the K in this case represents what we are calling the spring constant, the spring constant. Later on, we'll define what we mean by that term, the spring constant. So we are seeing that delta F over delta E is actually the F over E, which is the K. And we are saying that this K represents the spring constant. So easily we can see that delta F over delta E is equals to F over E, which is equals to K. And the K, remember, delta F over delta E in this case is equals to the gradient. So we can easily conclude that the gradient is equal to K. Why? Because the gradient is equals to F over E, and F over E is equals to K. So that implies that the gradient will be equal to K. And we are saying that this K, we are calling it the spring constant. So for a material that obeys the Hooke's law, we are concluding that the gradient of the graph of force against extension will always be equal to the spring constant. So the gradient of the force against extension graph will be equal to the K, which is equal to the spring constant. So this is very, very essential and paramount in calculations and also in practicals, because in a practical or in a calculation, somebody will just ask you to find the spring constant of the spring. So it is upon you to know that the gradient will always be equal to the spring constant. Alternatively, somebody can give you a data to draw the graph and obtain the gradient, then ask you, what does the gradient represent? So it is upon you to know that the gradient will always be equal to the spring constant. Later on, even if you compare the SI unit of the units of the gradient are the same as the units for the K, which is Newton per meter. Newton per meter. Now, what is this that we are calling the spring constant? So spring constant can be defined as a measure of the stiffness of a spring. Simply a measure of the stiffness of a spring. So that means the greater the spring constant, the stiffer the spring is. So stiff springs will always have a larger value of K or a larger value of the spring constant. We also have a few factors which are affecting the spring constant. So the first factor is the material of the spring. The second factor affecting the spring constant is called the cross-sectional area of the spring. The third factor is the thickness of the wire used to make the spring. The fourth factor is the length of the spring. Then the last factor is the number of turns per unit length. So in summary, you are saying that the 4 factors affecting the spring constant is 1, the material of the spring, 2, cross-sectional area of the spring, 3, thickness of the wire used to make the spring, 4, length of the spring, and 5, number of turns per unit length. Number of turns per unit length. So we've come to the end of our class today, but we need to discuss the quote of the day. So the quote of the day stated that we have 2 ears and 1 mouth, so that we can listen twice as much as we speak. Unfortunately, most of us usually speak twice as much as they listen. So what is the quote encouraging us to do? So the quote is encouraging us to listen to others with an intention of understanding what they are saying and not with an intention of replying. So we are saying that the quote is encouraging us to listen to others. That is, whenever you have a conversation with someone, listen to that person with an intention of understanding what they are saying and not with an intention of replying to what they are saying. Now, think about this. How many times do we get distracted by our devices, for example, mobile phones, when having a face-to-face conversation with someone? I guess many times. So in this case, we have given the other person our time, but we have actually denied them our energy, because our energy or our attention is on the mobile phone and not on the other person we are having a conversation with. So next time when you hear someone telling you to give them your time, just know that what they really want is your energy or your attention. And lastly, remember to always be slow to anger, quick to listen, slow to judge, quick to appreciate, slow to hate, and lastly, quick to forgive. So we've come to the end of our class. Thank you very much to my dear listeners. You've always been supporting me. You have always been there for me, even at periods whereby I've not been uploading a new video. I've always seen some constant positive comments, and I don't take that for granted. So I'll also beg you to hit that subscription button and also to turn on the notification bell, so that whenever I upload a new video, you will be the first person to get a notification on your phone or on your laptop or on your devices. Thank you very much. I wish you all the best. So let's meet next time. Thank you very much.